Welcome to this course where we will talk about recursion. To introduce this course, I want to talk about a game that you probably played before, the Tower of Hanoi game. We have n disks and 3 packs A, B and C, and the goal is to take those n disks from A to C, knowing that you can take one disk at a time and you cannot put a small disk on a big one. A represents the source pack, B represents the auxiliary pack, and C represents the destination pack. What if I tell you that given any amount of disks, we can get the steps to follow to win this game by using recursion? For example, if 1 is equal to 4, this is what we get. But before talking about it, let's first see what does recursion mean. A very important element in programming is the function, a block of code that eventually receives input, performs some instructions, and eventually returns an output. And a function can call other function, it's totally normal, but what if it calls itself? A function that calls itself is called a recursive function, and this is what recursion about, is the action of defining a function that calls itself. By following our intuition, we may think that the function will call itself again and again infinitely. You have to know that a recursive function has a condition where it stops. It's called the base case, we will talk more about it later. Now we go back to our Tower of Hanoi game. We want to move n disks from source to destination, and in order to do that, what we can do is that we move n-1 disks from source to auxiliary, we move 1 disk from source to destination, and we move n-1 disk from auxiliary to destination. And you can notice that inside the process of our move disk action, we are using the same action, which is to move disks. I know that it sounds weird, counterintuitive and all what you want, but after this course you'll become familiar with this idea, you will understand why do we need it, how does it work, how to use it, and many other things. If we follow our intuition, we may think that this process won't stop, because moving n-1 disks will require us to move n-2 disks, and moving n-2 disks will require us to move n-3 disks, and so on infinitely. But no, because after a moment we will reach the case where n is equal to 1, in other words, where we have only one disk to move, and in that case we just take it from the source to the destination we want. We don't need to call the same function again, we do it directly, it's what we call a base case. So a recursive function has a recursive case where it calls itself again, and a base case where it doesn't call itself again. It's necessary to stop the process at some point. And what we did here is that we use recursion to keep dividing the original problem, which is to move n disks from the source to the destination, until we arrived at small instances of the same problem, which are to move one disk only. I know that you probably didn't understand everything about what we did now, and you have a lot of questions, but don't worry, all of that will be explained in detail in the lectures of this course. Now let's see more examples on recursion. But before, you have to know that this course will be progressively released on this YouTube channel, but if you don't want to wait 2 or 3 months, you can buy the course and get access to the full course instantly. The link is in the description. Okay, let's suppose that you have a sorted array of integers and you are searching for the index of a specific value, let's say 6 in this example. And by comparing the search value with the element in the middle, you notice that the search value is smaller, so you deduce that the search value can only be in the left half because all values after the middle are greater than 6. This is why you repeat the same function but on the left half only. You compare with the middle and you notice that the search value is greater now. You deduce that it can only be on the right half. This is why you repeat the same function again but on the right half only. Now you compare with the middle and values are equal, so you finally found the searched value by using the power of recursion, because each time we call the same function but with a different input until we reach the base case where we found the element and we stop there. This searching algorithm is called binary search, by the way, and it works on sorted arrays only. You want another example? It's coming. Let's suppose that you have an array of integers like this one and you want to sort it, but the problem is that you don't know how to sort an array, you just know 2 things. The first one, you know how to merge 2 sorted arrays into a sorted one by always comparing the next 2 elements and taking the smallest, until there are no elements left. And you also know that an array that has less than 2 elements is already sorted, so you have nothing to do. If you followed well the first 2 examples, you'd guess that it's the base case, you'll see why soon. So by combining your knowledge, you decide that instead of sorting the whole array, you split it into 2 parts, you sort the left part, you sort the right part, and you merge them into a sorted array that represents the initial array but sorted. And this is what we want to get. But wait, now you face the same problem again, you don't know how to sort the 2 parts, so you decide to split them into 2 parts. But same problem again, you don't know how to sort all these parts, and what do? Splitting again. And you end up with having to sort these arrays of one element, but fortunately you know that they are already sorted, so you reach the base case. and now you have to start merging. So you merge these two, these two, these two, and now you sorted the left part of the original array. Right part now, you join these two, these two, these two, and you got the right part sorted. The last thing to do, you just join these two sorted arrays into one by taking 1, 2, 2, 3, 4, 5, 6, 8, and you get the original array sorted. This sorting algorithm is called merge sort. You can notice that we follow the same principle as the two previous examples. We kept dividing the problem into smaller instances of the same problem that are easier to solve until we reached the base case, and we joined results until we went back to the original function call, recursion. Another example, let's go. You have a file system made of files and directories, where directories can contain files and other directories like this one, and you want to get the total size. Know that the size of a directory is the sum of sizes of files and directories inside it. So in other words, we want to get the size of the main directory. Let's call it the root. And in order to do that, we sum the sizes of all files with sizes of all directories inside the root. Getting the size of a file is easy because it's one of its attributes, but to get the size of a directory, we have to get sizes of what's inside it. This is why this problem has a recursive nature. We have directories inside of directories, etc. And to solve this problem, we can use recursion. We keep getting sizes of directories by calling the same function over and over on each subdirectory until we reach the ones that have no subdirectories. You'll see the code in the next lecture. Now I want to talk about an important thing. If you already watched videos on recursion before, then the first examples of recursion you've heard about are probably factorial and Fibonacci sequence. And I didn't want to start the course with them as many other people do, because I consider that those are bad examples to introduce recursion. Let me tell you why. Let's start with factorial. Factorial n is basically the product of all integers from n to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, for instance. And it has a recursive nature because n factorial is n times n minus 1 factorial, and the base case is 1 factorial, which is just 1. So yes, I could introduce recursion with factorial function, and I know that it's easier to understand than Tower of Hanoi and merge sort. But the problem is that if you studied iteration before, which is probably the case, the first reaction would be to ask, why don't we just use a loop? Why would I bother myself using recursion instead of just using a for loop that calculates n factorial? And you'd be totally right, because even if we can show how recursion works with factorial n, you wouldn't get the point of using recursion instead of a simple loop. The second example is even worse, the Fibonacci sequence example. In the Fibonacci example, we want to get the value of the nth term of the Fibonacci sequence, where the nth term is the sum of the two previous terms. We also have the base case where n is smaller than 1, where Fibonacci of n is just n. And you can see that this example also has a recursive nature, because in the recursive case, the fib function is calling itself. But the same problem occurs here. We could easily get the nth term by using a simple for loop, so you wouldn't get the point of using recursion. And there is another problem with this example, its efficiency, because if we have a look at the function calls of Fibonacci 6, for example, we'd find a lot of redundant work, so this implementation will be slow. This means that not only Fibonacci can easily be implemented with a loop, but also iteration doesn't have this redundancy problem. So if I introduce recursion with these two examples, factorial and Fibonacci, you'd probably think that recursion is just an inefficient alternative to iteration, which is definitely not the case, because you'll learn how to optimize a recursive function later in the course. And also, not all problems can easily be solved with a loop. You can easily compute factorial of n and Fibonacci of n iteratively, but try to solve Tower of Hanoi iteratively. Try to implement merge sort iteratively, even if you can do it, but it's way harder than doing it recursively. A little recap, recursion in programming is when a function calls itself, and we can use it to divide a problem into smaller instances of the same problem and solving them by calling the same function over and over until we reach the base case. I know that you have a lot of questions in your head, how to determine the base case, how to write the code of a recursive function, what exactly happens when calling a recursive function, and so on. But don't worry, we'll be answering them in the next lectures. See you in the next one.